Usually when we talk about a medical diagnosis, there's this comforting expectation of precision, right?
Oh, absolutely. Like you break your arm, they take an X-ray, and boom, there's the problem.
Exactly. You see that jagged white line on the black background, and the doctor just points right at it.
Right. It's completely binary. Broken or not broken. You can literally see the fracture with your own eyes.
Hmm.
It's a highly visible, easily categorized problem.
But when you step into the world of engineering design, especially aerospace, that comforting certainty it completely vanishes.
It really does. It becomes incredibly murky.
Yeah, and suddenly you realize that even the most rigid-looking blueprints, like the ones packed with complex math and definitive schematics, they are often built on this really fragile foundation of human assumptions.
Which is terrifying when you think about it.
It is, because if those foundational assumptions are wrong, well, that broken bone is actually a massive rocket engine, literally tearing itself apart before it's even fully built.
Yeah, it's the absolute definition of diagnostic muddy waters. Except, instead of a plaster cast, you have thousands of gallons of highly explosive fuel on the line.
A slightly higher stakes situation, I'd say.
Just a bit. And today, we're looking at the absolute heart of a machine that is designed to operate in the unforgiving, incredibly violent vacuum of space.
Which is just wild to think about.
It is.
Yeah.
Engineering at this scale is ultimately about testing our very fragile human assumptions against the terrifying, immutable laws of physics.
And that brings us to today's source material, which is completely different from our usual fare. I mean, we usually look at history books or news articles, but today,
Today we have something a lot more dense.
yeah, we have our hands on a raw, highly technical engineering document. Specifically, we're looking at the V 2.0 design proposal for an 800 kilonewton liquid rocket engine.
It is quite the document to sift through.
It really is. And the mission of this deep dive is to explore one very specific, honestly incredible story hidden inside the pages of this technical manual.
A story about a very close call.
Right. We are going to see how a single, seemingly minor mathematical reality check completely revolutionized this engine's design.
And honestly, it saved the whole project.
Seriously. It was a single math check that saved this rocket from literally shredding its own insides the very moment they pressed ignite. So, okay, let's unpack this.
Where should we start?
Well, the title of the document says CEA verified open cycle, which, I mean, that sounds incredibly dense right off the bat.
It is a bit of a mouthful, yeah.
But before we get to the massive design correction, we first need to understand exactly what kind of machine we are trying to build here, right?
Absolutely. Because to understand the failure, we really do have to establish the baseline of what they were attempting to build in the first place.
So give us the baseline. What are we looking at?
Well, the design input for this engine calls for 800 kilonewtons of vacuum thrust.
Which is a massive amount of power.
Massive. And to achieve that kind of raw power, it requires a main combustion chamber pressure of 10 megapascals.
Okay, let me just pause there and translate that for you, because for those of us who, don't speak rocket science daily, 10 megapascals is roughly 100 times the normal atmospheric pressure you are feeling right now just sitting in your chair.
It's an immense amount of pressure. And if we connect this to the bigger picture of aerospace engineering, hitting 800 kilonewtons of thrust at that intense pressure, it puts our engine in the exact same heavyweight class as some of the most famous hardware in orbital history.
Like what kind of hardware?
We're talking about the exact thrust profile of SpaceX's Merlin 1D engine, or the legendary Russian RD-107.
Oh, wow. So this is not just some tiny little maneuvering thruster they use to gently nudge a satellite around.
Not at all. This machine is designed to act as the upper stage or even the main core stage of a major orbital launch vehicle.
Which means it obviously needs a serious, incredibly reliable fuel source to get all that mass off the ground.
Right, you need something with a lot of punch.
And the document outlines the propellant choice for this engine as LOX-RP1, which is liquid oxygen and kerosene.
A very classic combination.
Yeah, and I was reading through this, and I couldn't help but think of an analogy. Because kerosene, or RP1, as the aerospace folks call it, it's essentially the dense, highly reliable, relatively cheap multi-tool of rocket propellants, isn't it?
That's a perfect way to describe it.
Yeah.
The aerospace industry has relied on it since, gosh, the late 1950s for exactly those reasons.
It's just a workhorse.
It is. Now, RP1 isn't as theoretically powerful or explosive per pound as a fuel like liquid hydrogen,
Right.
but its density is its real superpower. Because it's a dense liquid at normal room temperature, you can pack an enormous amount of chemical energy into much smaller, tighter fuel tanks.
And when you are building a rocket, I mean, every single inch of tank space you can eliminate is less dead weight you have to drag all the way into orbit.
Exactly. It's a game of milligrams.
Right. So reducing the overall physical size of the vehicle by using dense fuel is a massive win for the rocket's structural design.
It is. And beyond just saving tank space, kerosene actually functions as a phenomenal liquid coolant for the engine itself.
Which we're definitely going to get into because that part blew my mind.
Oh, it's crucial when you're dealing with the kind of heat this engine generates. However, there is a distinct chemical quirk to RP1 that we really need to keep in mind because it sets up a major engineering hurdle later on.
Okay, what's the quirk?
RP1 has a known tendency for what the industry calls coking.
Coking, like leaving a sticky residue behind in the pipes.
Worse than that, think of it as a catastrophic chemical breakdown.
Oh, yikes.
Yeah. If RP1 gets hotter than about 450 Kelvin before it actually reaches the combustion chamber, the hydrocarbon chains start to destabilize.
So it basically cooks itself before it even burns?
Precisely. The fuel basically polymerizes and turns into this sludgy, solid carbon mess, and that will completely clog up the delicate plumbing of the engine.
Oh, wow. So you have this incredibly dense, highly useful multi-tool fuel, but if it gets just slightly too hot while waiting in the pipes,
It's game over.
it basically gives your rocket an instant heart attack by clogging its mechanical arteries.
That is exactly what happens. Yeah. Temperature control with RP1 is just an incredibly delicate dance. You have to keep it cool until the exact microsecond you want it to explode.
Right, so if RP1 is prone to melting down into carbon sludge, how on earth do you survive containing it in a chamber that is practically made of plasma? I mean, how do we efficiently direct all that explosive energy in the vacuum of space without melting the entire engine into a puddle?
Well, this brings us perfectly to the nozzle and the extreme cooling systems they designed.
Let's talk about the nozzle first.
Sure, the design dictates a nozzle expansion ratio of exactly 40.
Okay.
And just for sense of physical scale, that expansion ratio results in an engine exit diameter of about 1.47 meters.
So that's almost 5 feet across right at the base of the bell.
Right, it's a very large piece of metal.
But wait, I was thinking about this. If this engine is operating in the vacuum of space, where there is literally no atmospheric air pressure to push back against the exhaust, why not make the nozzle even wider? Like, why not use an expansion ratio of 80 to catch every last bit of that expanding gas and get more thrust?
You are hitting on a classic textbook engineering dilemma here. The principle of diminishing returns.
Ah, okay.
The engineers actually calculated the theoretical gains of a much larger nozzle in the proposal. Pushing the expansion ratio from 40 all the way up to 80 would theoretically capture more expanding gas.
Yes, but I'm guessing there's a catch.
A big one. It would only add about 3 to 5 seconds of specific impulse, which specific impulse is the metric used to measure engine efficiency.
3 to 5 seconds. That really doesn't sound like a lot when you were talking about orbital mechanics and millions of pounds of thrust.
Because it really isn't a lot. And the structural cost of chasing those few seconds of efficiency is severe.
How so?
Well, the engine would become significantly longer and therefore dramatically heavier.
Just to get that wider bell.
Exactly. And the added bulk would make it too large to fit inside the rocket's inner stage housing.
Right, the structural cylinder that connects the different stages of the rocket together.
Yes. So a ratio of 40 is actually the optimal compromise between perfect thermodynamic performance and physical real-world reality.
Got it. And the shape of the nozzle itself is something they call a Rao optimal bell nozzle. And I found this fascinating. They actually intentionally chop it off at 80% of its theoretical maximum length.
They do, yeah.
And again, doing that shaves off a lot of structural weight while somehow still maintaining 98% of the thrust efficiency. It really is all about aggressively shaving off every possible kilogram.
Weight is always the enemy in aerospace.
But honestly, the part of the document that absolutely stopped me in my tracks wasn't the nozzle. It was the combustion chamber itself.
The inner wall.
Yes, the inner wall, the physical barrier holding in the actual fire, is made of a zirconium copper alloy, and it is just 1.0 millimeter thick.
Very thin.
1 millimeter. I mean, 1 millimeter of metal standing between the cold vacuum of space and a 3580 Kelvin chemical fire. That just sounds like a typo to me. How is that physically possible?
The only way a 1 millimeter copper wall survives a 3500 Kelvin inferno is through a thermodynamic trick called regenerative cooling.
Okay, let me make sure I'm wrapping my head around this properly because I literally had to read this section of the document twice.
It is a bit counterintuitive.
Wait, so before we burn the highly flammable kerosene, we pump it backward along the outside of the incredibly hot nozzle just to keep the thin metal from vaporizing.
That's it exactly. It is a brilliant, completely closed engineering loop.
That is wild.
The engineers milled 120 tiny rectangular channels into the outside of that 1 millimeter copper wall.
Okay.
So before the cold liquid kerosene ever sees the inside of the combustion chamber, it is forced through those tiny channels at immense pressure.
Like a jacket of cold fuel.
Right. The cold kerosene absorbs the extreme heat radiating right through the copper wall. So the copper stays cool enough to remain structurally sound, and the kerosene gets preheated in the process.
Which I assume makes it burn more efficiently when it finally gets injected into the main chamber.
Precisely.
It is just elegantly violent. But wait, you mentioned the coking problem earlier.
Yes, the 450 Kelvin limit.
Right, so they have to keep that kerosene moving incredibly fast through those channels so it doesn't cross that 450 Kelvin threshold while it's absorbing all that heat from the wall. Otherwise, it just bakes into a sludge right there inside the wall itself, right?
Exactly. The fluid dynamics required to keep that fuel moving at exactly the right speed and pressure are staggering.
I can't even imagine the math involved in that.
It's complex. And
Yeah.
pumping that much fuel and oxidizer at 10 megapascals requires an unbelievable amount of raw physical power,
Right.
which brings us to the beating heart of the engine, the turbopumps. And more importantly, the critical flaw in the original version 1.0 design.
Because you can't just, plug a massive rocket pump into a wall socket. You have to generate all that mechanical power internally on the rocket.
Right. So to spin the pumps that source the main fuel and oxygen into the combustion chamber, this engine uses what's called a gas generator open cycle.
Okay, walk me through how that cycle works.
They siphon off a tiny fraction of the main fuel and oxidizer, ret it away from the main engine, and send it into a separate mini combustion chamber called the gas generator.
So they're essentially creating a controlled miniature rocket engine on the side just to power the pumps for the main engine.
That is exactly what they're doing. They ignite the fuel in there, and that mini explosion creates a high-pressure gas that spins a turbine.
Okay, making sense so far.
That spinning turbine is connected to a shaft, and that shaft mechanically drives the main pumps.
Got it.
Now, the document details that just to achieve the 10 megapascals of pressure for the main chamber, those pumps demand 3.6 megawatts of mechanical power.
3.6 megawatts just to move the liquid around inside the rocket.
That's a lot of power.
I mean, that is enough electricity to power a small town just for the pumps.
Delivering 3.6 megawatts requires a very, very aggressive spin on that turbine. And here is where the V1.0 design team made a near-fatal assumption.
Here we go.
When designing the metal turbine blades that would be blasted by the exhaust from this gas generator, the engineers manually assumed the temperature of that driving gas would be a very manageable 850 Kelvin.
Okay, so what does this all mean? Why 850 Kelvin specifically? Did they just, pull that number out of thin air?
It wasn't completely out of thin air. It was actually a widely accepted historical rule of thumb for uncooled turbine blades.
Oh, I see.
The engineers wanted to use a simple, uncooled metal turbine to save weight and reduce mechanical complexity.
Makes sense on paper.
Right. So they worked the problem backward. They knew their standard turbine metal could comfortably survive 850 Kelvin.
Right.
Therefore, they just assumed they could tune the gas generator to produce an 850 Kelvin gas without actually verifying the specific complex chemistry of LOX and RP1 at those extreme pressures.
Oh, wow. So by building the turbine, assuming the gas is exactly 850 Kelvin, they are essentially designing the engine blindfolded.
Pretty much, yeah.
It's like designing a car's transmission for a standard four-cylinder commuter engine, but someone secretly dropped a 1,000 horsepower race car engine under the hood.
That's a great analogy.
You are building the entire mechanical system based on a total guess about the sheer thermodynamic force that's going to hit it. The moment you hit the gas pedal, the gears are just going to shred themselves.
Exactly. That is the danger of relying on the way it's always been done without running these specific chemical reality checks.
Which, thankfully, they eventually did.
Fortunately, yes, someone decided to actually verify the math. To test their V1.0 guess, the designers took their exact parameters and fed them into a globally recognized standard.
Right. The document mentions this.
Yeah. NASA's Chemical Equilibrium with Application Software, or CEA.
Yeah, the document talks a lot about this NASA CEA software, and it mentions it calculates the minimum Gibbs free energy, which, I'll be honest, Gibbs free energy sounds like a term straight out of a sci-fi movie to me.
It does sound very futuristic.
What is this software actually doing to the numbers?
Well, in thermodynamics, Gibbs free energy is essentially a measure of the available energy in a closed system to do work.
Okay.
The CEA software doesn't care about human assumptions or engineering rules of thumb. It calculates the absolute most stable, natural resting point for a chemical reaction.
So it's just pure physics.
Pure physics. It looks at the specific molecules, the exact pressure, the exact ratio of the mix, and tells you precisely what chemical byproducts will form and exactly how hot that reaction will be at equilibrium.
The raw, unfiltered truth of the physics. So the engineers plug in their parameters, and they're using an extremely fuel-rich mixture in this gas generator, right? An oxygen-to-fuel ratio of 0.4.
Very fuel-rich. Yes.
So mostly kerosene, very little oxygen. They run it at 12 megapascals of pressure inside the generator. And the reality check that comes out of the NASA software is just staggering.
It was a huge shock to the design team.
The actual temperature wasn't the assumed 820 Kelvin. It was almost 1300. 1287.2 Kelvin, to be exact.
Yeah, a massive 51% increase in temperature over their baseline gas.
That is a colossal error.
And the thermal shock wasn't even the only problem.
There is more.
Oh, yeah. The specific heat capacity of the gas, which is the amount of energy required to raise its temperature, denoted in the math as its CP value, that was 3.42 kilojoules per kilogram Kelvin.
Okay, what does that mean in practical terms?
It means it had a 71% higher energy capacity than they had factored into their entire V1.0 blueprint.
Okay, here's where it gets really interesting. I have to push back on this for you because reading the document, it feels incredibly counterintuitive.
How so?
Well, how could the original engineers be that wildly wrong about the temperature? They were running an OF ratio of 0.4.
Right.
That is heavily, heavily fuel-rich.
Yeah.
There is nowhere near enough oxygen in there to actually burn all that kerosene. So shouldn't drowning the fire in extra unburned fuel basically smother it and make it cooler?
This raises an important question, and it perfectly illustrates why human intuition completely fails at extreme thermodynamic margins.
So I'm not crazy for thinking it should be cooler.
You're not crazy, but the hidden chemistry of RP1 is incredibly complex.
Yeah.
It isn't just a simple block of carbon. It's a dense, tangled web of hydrocarbons.
Okay.
When you introduce it to an oxygen-starved, highly pressurized environment, the carbon itself might not fully combust, but the hydrogen atoms absolutely do.
I see.
The hydrogen components in the kerosene rapidly react and burn, and hydrogen combustion releases massive, concentrated spikes of heat.
Oh, wow. So the carbon is just sort of hanging around, maybe forming some soot, but the hydrogen is basically having an absolute thermite party.
That's a great way to picture it.
Yeah.
Furthermore, that highly energetic hydrogen reaction produces a high volume of low molecular weight gases, specifically pure hydrogen gas and methane.
Okay, and why are those gases a problem?
Because gases with very low molecular weights naturally possess extremely high specific heat capacities. They act like thermal sponges.
Oh.
So not only is the fire inherently hotter than they expected, the resulting gas cloud is capable of absorbing, holding, and transferring a drastically higher amount of raw thermodynamic energy to anything it touches.
Oh, man. We now have a gas slamming into our turbine that is astronomically hotter and way more energetically dense than they planned for.
Exactly.
Let's look at the catastrophic domino effect here. What if they hadn't run that NASA software? What happens if they actually try to build and ignite the V1.0 turbopump with this new 1287.2 Kelvin reality?
The engine would have consumed itself in a fraction of a second.
Seriously, just instantly.
Instantly. To understand why, we have to look at something called the ideal specific work.
Okay.
This is the measure of the raw kinetic energy available in the gas to actually push the turbine blades. In the V1.0 design, the engineers calculated the gas held 948 kilojoules per kilogram of energy.
But the NASA CE reality proved it was actually 2,455 kilojoules per kilogram.
Right.
I mean, it's a 2.6 times increase in sheer physical energy.
Then to efficiently absorb and extract that massive 2.6 times increase in energy, a single-stage turbine, which is just one single wheel of blades, would be forced to spin at a terrifying speed.
How fast are we talking?
The mathematics show that to process that much kinetic energy, the blades would need to reach an optimal peripheral velocity of 886 meters per second.
Okay, let me translate that into a vivid disaster scenario for you. 886 meters per second is over Mach 2.5.
It is incredibly fast.
At rotational speed, you are fundamentally violating the physical tensile strength limits of aerospace metals.
Completely.
Even the strongest alloys generally cap out around 500 meters per second before centrifugal forces simply rip the atomic bonds apart.
Yes, the metal just gives up.
So if they had built V1.0, the very moment they ignited the gas generator, that single-stage turbine would spin so insanely fast that the centrifugal force would literally shatter the solid metal blades like glass inside the casing.
Total destruction.
It would turn the turbopump into a literal fragmentation grenade.
A total catastrophic structural failure, yes.
Yeah.
But, even if we pretend the metal possessed some magical tensile strength and didn't shatter from the physical spin rate, the thermal reality would still doom the rocket anyway.
Really?
Right.
Because of the heat alone?
Oh, absolutely. The uncooled metal blades they originally planned to use have a thermal melting limit of around 1,000 Kelvin.
And the gas hitting them is 1247.2 Kelvin.
Precisely. The blades wouldn't just shatter. They would be turning to liquid at the exact same moment they were being ripped apart by centrifugal force.
Wow, that is the ultimate bad day at the test stand.
It would have been a very short, very expensive test.
So, armed with this terrifying, blade-shattering NASA CEA data, the engineers obviously had to go back to the drawing board.
They had no choice.
Right. How do you redesign the engine's heart to handle a gas that is this energetic and this blisteringly hot? The V2.0 fix they came up with is just an elegant piece of engineering.
It really is beautiful work. The solution to the speed problem is pure mechanical ingenuity. Fix number 1. They completely abandoned the single-stage turbine.
Makes sense.
They replaced it with a two-stage velocity compounded turbine.
Which means basically 2 separate wheels of blades on the same shaft instead of just 1 wheel, right?
That's right. By forcing that ultra-high energy gas to pass through a first row of blades, and then redirecting it through a second row of blades, they effectively split the mechanical workload in half.
Oh, that's smart.
Neither stage has to spin at that impossible Mach 2.5 velocity to extract the necessary energy. And the underlying physics of splitting the pressure drop across 2 stages means each stage requires a much lower peripheral velocity.
Okay, so it doesn't shatter.
Right. And because they need less velocity, the engineers could actually shrink the overall physical diameter of the turbine discs.
Wait, they made it smaller?
Much smaller. It went from an 877 millimeter monster down to a highly compact 598 millimeters. That is a 32% reduction in physical size.
Which translates to massive weight and space savings for the rocket.
Exactly, which is always the goal.
But wait, that doesn't solve the heat problem. You still have 1287.2 Kelvin gas slamming into those smaller blades.
True, which leads us to fix number 2. The era of uncooled blades was officially over for this design.
They had to bite the bullet.
They did. They upgraded the turbine material to advanced nickel-based superalloys, and they introduced active cooling.
How do you actively cool a spinning turbine blade?
They engineered minute internal convection channels and film cooling pores directly into the structure of the turbine blades themselves.
That sounds incredibly difficult to manufacture.
It is, but this constant flow of coolant ensures that even though the gas hitting them is nearly 1300 Kelvin, the actual metal of the blades remains safely below 1050 Kelvin.
So they essentially built miniature versions of that regenerative main combustion chamber wall right inside the spinning turbine blades.
Basically, yes.
That is just brilliant. But, the absolute best part of this whole V2.0 redesign, the absolute cherry on top, is the hidden bonus they discovered.
In the flawed V1.0 design, the engineers calculated they would need to siphon off 2.61% of their total main fuel and oxygen tank capacity just to feed the gas generator.
Which is a pretty standard tax for an open cycle engine, right? You have to burn some fuel just to pump the rest of the fuel.
Exactly. It's the cost of doing business. But with the NASA-verified hyperenergetic gas in V2.0, that mass flow requirement plummeted.
How far did it drop?
Dropped from 2.61% down to a mere 0.93%.
I mean, that is a drop of over 60%. And because this is an open cycle engine, the exhaust from the gas generator is just dumped overboard after it spins the turbine.
Right, it's mostly wasted.
It provides a tiny, tiny bit of thrust, but it is basically wasted fuel. Now, because they need drastically less fuel to run the pumps, that extra fuel, that 1.6% difference, gets piped directly into the main thrust chamber.
It's incredible.
They practically got free performance.
It is a tremendous engineering victory born from what was almost a disaster. By routing that saved propellant into the main combustion chamber, they actually boosted the engine's overall specific impulse by 1 to 2 seconds.
Which, as we established earlier, is a very big deal.
Huge deal. The crisis, the terrifying realization that their foundational math was completely wrong. It forced a redesign that made the final engine significantly better.
Yeah.
It's physically smaller and thermally more efficient.
What an absolute incredible journey from blueprint to reality.
Truly.
To summarize this for you, we started with a massive 800 kilonewton engine and a design team that relied on an old, comfortable engineering rule of thumb, assuming a neat, tidy 850 Kelvin gas.
A comfortable but deadly assumption.
Right. Then came the NASA software intervention, revealing the chaotic 1287 Kelvin blade-melting reality of their chemistry. And that harsh reality check culminated in a V2.0 engine that is smaller, smarter, actively cooled, and fundamentally more powerful, outputting that perfect 800 kilonewtons of thrust.
Physics simply doesn't care about our assumptions.
It really doesn't.
But before we wrap up today, I want to leave you with a final thought to mull over.
Please do.
We saw how this V1.0 engine almost failed catastrophically, simply because of an unverified engineering rule of thumb. In our modern era of endless data, dashboards, and information overload, it makes you wonder, in our own professional lives, or even in our daily routines, what rules of thumb are we operating on right now that desperately need a reality check?
That is a great point.
What assumptions are we building our own blueprints on simply because that's the way it's always been done?
That is a phenomenal question to carry with you. Thank you so much for joining us on this deep dive. Keep questioning the blueprints of the world around you, and we'll see you next time.
And remember, sometimes that diagnostic X-ray machine really is broken, and you just have to do the math yourself.